Dear friends, Aspirants is a collective of mathematics students, research scholars, faculty members across India, started by myself in 2017. And we used to organize online problem solving sessions, test series, and online webinars to help the students who are pursuing higher mathematics. As a part of the online problem solving session series, today we have a session on differential calculus, and we're blessed to have Ms. Nandana K. Vasudevan with us to handle the session. Ms. Nandana did her master's from Cochin University of Science and Technology, Kerala, and currently pursuing PhD at ℕ𝕒𝕒𝕣𝕥 Vidyapeetham, Coimbatore, Tamil Nadu. And her basic broad research area is graph theory. So today she will discuss some basic aspects of differential calculus and previous year questions regarding in that particular area. So I welcome everyone to this program, and I express my gratitude to Ms. Nandana for being with Math Aspirants. I think this is the 5th or 6th session that she is handling in our platform. So once again, I welcome everyone to this program. Welcome, Nandana.
So good evening to all the participants out there.
Okay, so my topic of presentation for today, like sir has introduced, is differentiation. And like he said, I am not a new resource person to maths aspirants. In fact, this is the 6th session that I am handling. So these are the videos that I've done earlier. So I have handled sessions in limits and continuity, like 2 sessions in that, then matrices, and in sequence and series. So these were taken long back in the sense like the first 3 videos are dated to 2021 and the other 2 are from 2022. Due to time constraints, I was not able to handle any sessions in 2023 or 2024. So I have those constraints even now, but since sir asked, I thought, okay, I'll just go ahead with it. So it will be like a revision for me myself as well. So I thought I'll go ahead this time. So like already mentioned, our topic is differentiation. And I believe most of the people who are in the session, they'll be students who are preparing for their JAM exam, which is to come next year, right? That is JAM 2026. And this time, the organizing institute is IIT Bombay. And this is the syllabus that was given in their website. And like you can see, I have already underlined some parts in blue, and I'll be handling only those topics for this session. Okay, so they are differentiation, Rolle's theorem, mean value theorem, maxima, and minima. And I have excluded the session of Taylor series and Maclaurin series for the time being. And those who are interested, you are free to look at the class video that I've already taken on limits and continuity. So there are certain things related to ℕ-L'Hopital rule, which is already included in that video, and you're free to look into it. Okay. All right. So we'll start the session formally now. Moving on to the session, my way of taking, I'll be just recalling the things that you have already learned. Maybe you would have already learned these things in some other semester. I think students of first year, second year, third year will all be there. So some would have learned it in their old semesters. So you would have forgotten certain things. So we'll just recall the things that you have already learned, and then we'll move on to some previous year questions. Okay, so that will be the method that I'll be following. And most of the time when we are taking a class, we have that the teacher is always active and the students are always passive. So I expect active participation from your side as well. Okay, so we can share the details mutually. When we are moving on to problems, particularly, we'll need ideas from different angles. So I would have done my problem in some way. If you have done it in some other way and you have received the same answer, then you're free to give that idea. Okay, so that's how we'll be moving with the session. And let me start recalling the topics. So the first thing, like the statement, is derivative of a function. So can someone tell me what is derivative of a function? in either in general or at a particular point or in a given domain? So can any one of you just give me an idea of what it is?
It is the slope or the gradient at a point over a several point which we the several point ka set is called domain.
Yes. Okay. On one side, it's right. So on the geometrical aspect, he has said that it's the slope. And any other formal definitions to be given by anyone else?
It is a rate
It's the
change
change.
measure.
It is the rate of change. Okay. So maybe we can use that concept when we are moving to physics. All right. Now, any other definition? Let's go to the proper mathematical definition. So do you know something which is given in terms of epsilon, delta, all those things? So we have such a definition for continuity, and we have something similar for derivative as well. So this is the definition. So here what we have is that if I am given a function, say f, so it can be defined either on set of real numbers or some interval. Okay. So on such a given domain, I have defined my function f, and at some point in that interval, say c, I am trying to find out the derivative. So what is its derivative? If I'm taking a point in a very close boundary of this point c, say x, I have that the difference between f of x minus f of c by x minus c and L, where L is the derivative at that point, the difference is arbitrarily small enough. So just like how you say for continuity, when you're saying about continuity, it will be like you have a point C, you are taking some point X, which is very close to C, you have that f of x will be very close to f of c. So in a similar way, we have given the definition for derivative as well. So instead of f of c, or f of x and f of c, you are taking f of x minus f of c by x minus c and L. All right. Then we say that at that given point, f is differentiable. And if the function given is f and the point at which we have to check the derivative is c, we denote it by f dash c. And if you are using the idea of limit, we have that f dash c equals limit x tends to c, f of x minus f of c by x minus c. So this is something very important, and this is the thing that we'll be using throughout. The definition given earlier, that is the concept, and the problem part, you need this particular equation or formula, whatever is given. All right. And now, interpretation of derivatives. So in the previous slide, what we said was derivative at a particular point. So in general, what is derivative? If I'm saying simply f dash of x, it is limit h tends to 0, f of x plus h minus f of x by h. That is, in some close boundary of x, you are taking some other point, say x plus h. All right. And now we are moving on to the geometrical interpretation of derivative, which was the answer given by the person who said first, which is the slope of the tangent at any given point. So let's say you are given the function f, you are asked what is derivative at point C. So what you have to do is you take the function f, you draw the graph of that function, you will get something within the Cartesian plane, and there you will have to take the tangent. So I think tangent is something that is known to all of you. So if you are asked at some point C, you draw the tangent at that particular point on that graph, and whatever is the slope of that tangent, that is same as the derivative obtained at that point. So that is the geometrical side of derivative. So geometrical side, it's not from exam point of view, it's completely from theoretical part. Okay, so since I'm recalling the things, I decided, okay, I'll discuss this as well. And then, how is differentiability and continuity connected? So when we are starting the paper of calculus, we say limit, continuity, differentiability. They come as a combo pack. So limit, okay, we make use of limit to define the definition of continuity and differentiability. But what about continuity and differentiability to each other? How are they related? Is there a kind of implication there?
Every differentiable function is continuous, but not
Yes,
every continuous function is differentiable.
exactly. Very good. So every differentiable function is continuous, let's say at a point or in a given domain, whatever. So I think I forgot to define the concept of being differentiable in a given domain. So that is again very much analogous to the concept of being continuous. So when you're saying continuity at a point, we define continuity at a point first. Then when we talk about being continuous at an entire domain, we say that if the function is continuous at every point in the domain. In the same way, in a domain, we have that the function is differentiable if it is if it has a derivative in every point in its domain. So very same concept. Okay. So now, like he said, f is differentiable at C would obviously point to the fact that f is continuous at that point, but the converse is definitely not true. So f is continuous at a point need not imply that f is differentiable at that point. So there arises a question. Under what all conditions is the function not differentiable? Let's say it is already continuous. So if it is not continuous, obviously the differentiability condition is affected there. In case it is continuous, under what conditions is the function not differentiable? So can you give me some examples for that?
mod x,
Mod x, yes. Any other functions?
greatest integer function,
Greatest integer function, okay. So greatest integer function is basically not a continuous function at all. But mod x is continuous, but not differentiable at x equal to 0. So there you have some conditions, like some structures are there for the graph of the function, which violates the condition of differentiability. So we are moving to that part, that is non-existence of derivative. So here we are not going to discuss more about discontinuity because that is something very trivial. So we'll talk about the other three, that is corners, cusp, and vertical tangents. So corners, they are the example for mode function. So these things, the idea of the first two examples, that is corners and cusp, there the idea is that, let's say you're trying to take the derivative from one side, from the left side, and from the right side. So most of the time derivative does not exist at that corner point, that tip. So the problem there is that when you try to take derivative from one part, you'll have a tangent along that side. When you're trying to take it from the right side, you'll have a tangent there as well. So let me just show it to you. So let's say, okay, I have this particular example. So I'm taking my f dash here. So the tangent is going on like this. And at this point, with respect to this graph, I have my tangent like this. And with respect to this graph, my tangent is like this. Which means at a single point, you have two different tangents of different slope. So which means you have a problem to decide which is the accurate tangent for that point. So that is the problem caused when it comes to graphs like this. And vertical tangent is the case when slope becomes infinity. So most of the time, conventionally, when we speak in mathematics, anything that comes as infinity is not defined. So in a similar way, we can say that for vertical tangent cases, we don't have derivative doesn't exist. And discontinuity, it's already something we have already spoken about. So now we move on to the first application related to differentiation. So we are only going to talk about these prominent applications, among which first one is first derivative test. We have something called a second derivative test as well, which we'll be seeing soon after the slide. So what is first derivative test? What is its utility?
To find the critical points.
To find the critical points, okay. Any other applications?
To find local maximum and local minimum.
Local maxima and local minima, very good. Anything else? Can you say something about the structure of the graph or as a whole of the function?
Whether the function is increasing or decreasing. To determine whether the function is
Yes.
increasing or decreasing.
Yes, exactly. Very good. So these are the core things that comes under first derivative test. So when we are using first derivative, so everything depends on the question that is given to you. Based on the question, you have to define whether you should be taking first derivative test, second derivative test, or both. So we'll see first derivative test for now. So here, like the name states, we are going to talk about first derivative only. Okay, so we are talking about f dash. So a point at which f dash becomes 0, that point is always a local extremum. So let me highlight my point. It's a local extremum. I'm not saying it is a maximum or minimum. I haven't decided it so far. Okay, it's merely a local extremum. And then if f dash is greater than 0, we have that the function is increasing. And what is left? F dash is less than 0. So there f is decreasing. So anyhow, for any number you take, it has the trichotomy property. That is, it is either 0 or less than 0 or greater than 0. So we have sorted all the three possible cases. So when it is 0, it is a local extremum. If it is greater than 0, f is increasing. And if it is less than 0, f is decreasing. So that's about first derivative test. So that's all. And this is a small illustration of the theorem. I don't know if the green lines are visible to you enough or not. So you can see I have drawn a wave graph, something kind of a sine graph, but not exactly sine graph. I have shifted it right and top. So I have made slight changes. So that's a graph there. You can see that my f dash is initially greater than 0 since it is increasing. It reached at an extremum. So my f dash became 0, which is at point A. Then it decreased. Then so my f dash became less than 0. Again, it came back to f dash 0 at point B. And again, it increased. So this is an illustration of the first derivative test. And next, we'll be looking at second derivative test. So like the name states, we are going to work with second derivative. That is derivative of derivative which is already taken. So you have f dash, you take derivative again, you get f double dash. So we are going to work with f double dash when it comes to second derivative test. So here, what is second derivative test? Again, answers are welcome from the participants. I'm happy that you people are responding. Okay, so answers please for second derivative test. What is the utility?
To find maxima.
To find maxima or minima, okay.
Also the
concavity.
Yes, very good. So that is the core applications of second derivative test. That is to identify maxima and minima. I would not say find maxima or minima, to identify maxima or minima. And then secondly, to analyze the structure of the graph. How is its shape? When you're trying to draw the graph, how will its shape look like? Kind of. We are not going to give an exact structure. If you have to know the exact structure, you'll have to draw it itself. Okay, there is no other option for that. But to at least get an idea, because when you are given problems, they give very complicated functions. It may not be something that is always constructible for you, right? We can draw sine, cos, tan, then let's say exponential function, log function, polynomial function to an extent. So all these things you can draw. But what if they are giving something bigger than that, or as a combination of these? So it's not practically possible to sit and draw it. So there you make use of these kind of tests to understand the structure of the graph. So when you did first derivative test, you already saw in which all regions it will be increasing, in which all regions it will be decreasing. All those things you have seen. So in a similar way, when you make use of second derivative test, you will get to know where all it is concave, where all it is convex. All right. So there we are moving to the divisions again. So if f double dash is 0 at some point, we call that point as point of inflection. So point of inflection is the point at which the concavity changes. That is, it changes from concave to convex or convex to concave. Okay. So that is called as a point of inflection. We'll see example as well. So that is the first thing. And if f double dash is greater than 0, then the graph will be concave up. I'm not going to use concave and convex because it depends on people how you are drawing concave and convex. So let's not confuse it as a or make a mess of it. We'll use concave up and concave down. So concave up, it will look like the union symbol. That is, it's open towards upside, and concave down, it will look like intersection symbol. So it is open towards the bottom side. Okay. So f double dash is greater than 0 means in that particular region, we'll have the function as concave up. And when f double dash is less than 0, we have it as concave down. All right. So it's time to see an example. Same graph that I used in the previous example for first derivative test. So there you can see that I have a part of graph which is concave down and a part where it is concave up. So throughout that region, one part is f double dash less than 0, while remaining part is f double dash greater than 0. And that single point where my concavity has changed from concave up to concave down. Okay. So in that point I have marked as C, and that point has f double dash value as 0. So that is my point of inflection. So even though the term looks slightly confusing or slightly complicated, idea is very simple. The point at which concavity changes. That's it. All right. So now we are done with defining first derivative test and second derivative test. So now our application is local maxima and local minima. So in this case, we will be combining these two tests together. So like I said, the question given to you, that will demand what is required. If you are merely asked where all the function is increasing, where all the function is decreasing, then first derivative test is enough. If you are asked about concavity or points of inflection, second derivative test is enough. In case you are asked about local extremums, then you will require both. So how is it useful? So let's say I have computed my f dash value and I have filtered out the points at which my f dash is 0. So like said, we have that the points at which f dash is 0 will be local extremums. So we don't know whether it is maximum or minimum. So for that classification, we'll be making use of second derivative test. So let's say my f dash value is 0, but f double dash is positive. In that case, my point, whatever x0 is taken, that will be a local minima. And similarly, again, when f dash is 0, but f double dash is negative, I'll have that x0 will be a local maxima. All right. So here, the same graph again. This is the illustration. Okay. So this is how it looks like. So depending on whatever is the question given to you, we'll decide whatever things needs to be given. Okay. So it doesn't mean that you are taught all this, you have to apply all this as junk. Look at the question, what is demanded, what is asked, based on that you give the idea. All right. So now there were two more topics included in my section, which are Rolle's theorem and mean value theorem as well. So we are going to Rolle's theorem. These two come as a combo always. We say these two together every time. So what is Rolle's theorem? Anyone to give the statement? You may miss out conditions, but that's fine. I'll give the formal statement. But does anyone want to give the statement before that?
Ma'am, I can just give the formula. Like,
Yeah, sure. Go ahead.
f dash of c is equal to f of b minus f of a by b minus a, if a and b are the endpoints of an interval.
Okay, so is that Rolle's theorem or mean value theorem?
Mean value theorem.
Yes. So there is very slight difference between Rolle's theorem and mean value theorem. What you said now is the formula that comes in mean value theorem. So what is Rolle's theorem?
Ma'am, fx is a continuous in closed interval a to b
Mm-hmm.
and differentiable in open interval a to b.
Yes.
Then there exists c
Mm-hmm.
such that differentiation of function at c equal to 0.
Yes,
There
very
is a
good.
condition, ma'am, f of a is equals to f of b, ma'am.
Yes, exactly. So that was one small condition that was missed out. So now I don't know whether one person has said or two of them answered. What was it?
I answered mean value theorem's formula.
Okay, so okay, whatever. So those people who have answered, thank you for the response. So we'll revise mean value theorem as well. So Rolle's theorem, they have given the formal statement now. So I have a function which is defined on a closed interval AB, and there are three different conditions on that. One is that function is continuous in that given domain. Then it is differentiable in open interval AB. And third one, f of a and f of b are strictly zero. Then the conclusion is that there exists a point in that open interval AB such that at that point my derivative is zero. That is Rolle's theorem. So here, when we are looking at the interpretation of that theorem, you can see that this is how it looks like. That is, you have a graph of a function given here. So here you can see that f of a and f of b are 0. And what happens? There is a point c at which my derivative has become 0. So let's say I am talking about the graph except f of x equal to 0 for all x. Okay, we are not talking about that graph. We are talking in general. Okay, so in that case, if I have a graph which crosses the x-axis twice, between those 2 points, there will definitely be a maxima or a minima. That is what we can say in extreme geometric aspect. Okay, so you are trying to draw the graph. There are 2 points at which the graph crosses the x-axis. Then between those 2 points, there will always be either a maxima or a minima. All right, so here I have drawn maxima. You can draw it like this as well. So here you will have minima. So that's also possible. Okay, so that is Rolle's theorem. And mean value theorem, already someone has given that answer. So that is very small difference between these two Rolle's theorem and mean value theorem. So what is the difference here?
In mean value theorem, this f of a and f of b need not be equal to 0.
Exactly. So it doesn't demand the idea that f of a and f of b should be 0. If at least one of them is non-zero, you can make use of mean value theorem. So there also again conditions, initial conditions are same. That is, the function is defined on a closed interval, and in that interval, the function is continuous. You are taking the corresponding open interval, the function is differentiable. And then, like said, f of a and f of b need not be 0. So then there exists a point in that open interval AB such that the derivative at that particular point will be f of b minus f of a by b minus a. So can someone tell me the geometrical side of this mean value theorem, like how I given the Rolle's theorem geometrical interpretation?
If we, excuse me, ma'am, I'm saying.
Yeah, go ahead.
If we draw, yes, if there is a curve f of x, suppose I'm considering the interval closed AB. In case the point, if we join the point A, comma f of A and point B, comma f of B, then the slope of this chord, there exists at least C for which the slope at that point is equal to the original chord.
Very good, very good. Excellent. So that is the very same answer that is required. So let's say I am given this function. Okay, so we already have the domain, which is closed interval AB. Okay, I have the graph drawn for that function as well. So let's say I am just merely drawing the line connecting A f of A and B f of B. So there will be a straight line and that line has a slope also. And this theorem states that there exists some point in the open interval AB such that the slope of the tangent at that point will be same as the slope of this line. So I'll show you the image of that. It will look something like this. Okay, so this is A f of A and B f of B. Okay, and you can see that the lines, the blue lines are already parallel. Okay, so which means they are having the same slope. Okay, so here maybe you can make use of the idea you have learned in geometry. So let's say I have 2 points x1 y1 and x2 y2. So if you are trying to find the slope of the line connecting these 2 points, it is m equals y2 minus y1 by x2 minus x1, or same as y1 minus y2 by x1 minus x2. So same idea. So let's see, you can see that this is same as whatever is given here. So here my x1 and x2 are A and B, while y1 and y2 are correspondingly f of A and f of B. All right. So it's the same. So this is the statement for mean value theorem, and that is the geometrical interpretation. So with that, we are done with the theory part. So do you have any doubts? We'll be moving to the problems next.
No doubts, ma'am.
No doubts, ma'am.
So is the ideas clear enough?
Yes, ma'am.
I don't know if I was moving too
Yes, ma'am.
fast.
Clear.
No, you are in a normal pace. No problem. We'll go ahead with
Okay.
problems.
Okay, thank you so much. Okay, so now it's time for some problems. I know it's not good to hear about problems, but since I'm assigned this work as well, I should be dealing with some problems. All right. So yes, so we'll be applying these ideas. Okay. So I have gone through question papers, JAM question papers from I think 2019 to 2025. Okay. So which are very much straightforward. I haven't taken those questions. Only those which require some kind of an acceleration or a push from a side. I have taken only such questions. Okay, clearly direct questions, it doesn't require my assistance at all. Okay, and before we move to the problems, I have certain things to say. So one thing is that it need not be that the question given to you is always involved in one single topic. Okay, the question may look like it requires only some concept, but sometimes depending on the options, you will have to make use of multiple concepts. Okay, sometimes you will have to use first derivative and second derivative, or some other ideas as well. You'll have to incorporate multiple ideas. So based on that, we'll read the questions. Okay, and in some questions, when you are trying to prove, in some questions, it is easy to give some counter example. You give some counter example, you will be able to strike off some wrong options. So we'll be following that method as well. Okay, so you're free to use any method, but make sure that you are using very less time. Okay, because time is a very big factor when it comes to competitive exams. So make sure that whichever method you are using, it requires minimum time. Okay, so now we'll move to problems. Again, I am requesting you to keep on giving answers, suggestions, whatever you have with respect to the question. Okay, so we start with the first question. Since I don't want to trouble you all of a sudden, I have started with a simple enough question in the beginning. So this was the question that appeared in the JAM exam just the year before. You have two huge functions in front of you, f and g. The question is concerning differentiability of f and g at x equal to 0. Okay, so they are just, the options are merely combinations of these. So you have to check the differentiability of f first. So you will get two options are already striked off from the list. Then you check for differentiability of g. All right. So we'll just start with derivative of f at x equal to 0. So I'll give you a minute or so. Maybe you can just calculate it there parallelly. And I would like to know the answers. If you get the answer, you can either unmute yourself and say the answer, or you can put it in the comment box. I can view it here parallelly. So if anyone has got the answer, you can just say that. The question is whether f is differentiable at x equal to 0. So anyone has got any answers? So it's probably an yes or no. Okay, so an answer has come as C, that is both f and g are differentiable at x equal to 0. Okay, any other answers?
Ma'am, I feel it's D.
D. Okay, so that person is completely contradicting the answer of the one who has already told first. So she's saying both are not differentiable. Okay, any other answers? Anyone going for A or B? Am I audible? Okay, so 1A has come.
Ma'am, eighth is differentiable at 0, but where g should not differentiable at 0.
Okay, so again another option A has come. Any other answers? So no one is going for B. A, C and D has come. Okay, again D, A, okay. So I guess when you are giving the options, you have computed the derivative of both functions. Okay, that's good. All right, so option A is coming up more and more. So this is a starter question. So before we
Option
have
A,
a
ma'am.
great meal, yeah. Okay, option A again. So before we move to a great meal, we have starters, right? Just like that, I have given a starter question, which is direct enough. So can we move to the answer part now? I think we'll look at F first. Okay. So this is the first part, which is for F. Okay. So we are making use of the formula that I gave in the very first slide. So f dash of 0, it is limit x tends to 0, f of x minus f of 0 by x minus 0. That's merely from the definition. So I have substituted my f of x and f of 0. And you can see that the zeros, they are not making any difference to the numerator and denominator. So here x and x gets striked off. And what remains is limit x tends to 0 mod x mod sine 1 by x. So I have given a 0. How did it become 0?
Limit x tends to 0, therefore x equal to 0.
Mod sin x is bounded function.
Sine 0 equal to 0.
But it's not sine 0. It is sine 1 by 0.
But on sin 1 by 0 is bounded function. So
Exactly. That is the point that is there. So here there are two functions. You can see it's the product of two functions. One function is already tending to 0 and the other one, it is bounded. So sine function is basically bounded, but sine 1 by x is slightly problematic. Okay, sine x, it's quite easy, I think. So it will look like this. Okay, a pretty enough wave function that is bounded between 1 and -1. But what about sine 1 by x? Its structure is slightly different. So let me just draw sine 1 by x here. So it will look like, so here you have 1 and -1, and from some point it is coming like this, and towards 1 the oscillations are very close, and towards this side also we have like this, and this is how sine 1 by x looks like. So this is my sine x and this is my sine 1 by x. So sine 1 by x limit at 0 is not defined, because you can see here it is oscillating. Let me take a different color here. So at 0, at this point, it's oscillating very fast. So you cannot decide whether it is 1, -1 or some other value between that. So there you cannot define the limit of sine 1 by x at 0. But since it is bounded, we have that limit, this whole limit is 0. All right. Is that idea clear?
So, ma'am, you're trying to say that we don't have to consider sine 1 by x in this case. Like, we
Yes.
don't need to have, there is no need for us to apply 0 in place of x in sine 1 by x.
Yes, exactly. So since that is a bounded function, you need not bother about that now. Okay. All right. So now we have that. Okay, let me keep my pen aside. Okay. So now we have obtained derivative of f at 0. So you have that as 0 already. So we have that f is differentiable at x equal to 0. So now we have to focus only on options B and C. B and D, I think. Okay, so A and C were options constituting differentiability of x at 0. So now we have to focus on G. You have to sort whether G is differentiable or not. So is G differentiable at x equal to 0? What do you think? So we already have the answers, like many answers have come as A, C and D has also come. So let's have a look at G now. So this is my G. Again, the first step is merely the formula. So there we have given G dash 0, and like I have done it for F, I have substituted my function there. Okay. So it's x square sine 1 by x plus x cos 1 by x minus 0. So again, you can see that x is common to both the terms. So there it becomes limit x tends to 0, x sine 1 by x plus cos 1 by x. So it is sum. I have just taken a break with respect to that addition. So I have taken limit x tends to 0, x sine 1 by x and cos 1 by x. Now what happens? Till there it's fine. What next? So limit x tends to 0, x sine 1 by x can be treated in a similar way as how we have done for the previous function, that is for f. So this is already tending to 0 and this is bounded. So that becomes 0. What about limit x tends to 0 cos 1 by x?
That's also bounded.
Yes, it is bounded. What about the limit at 0?
But it is not defined.
It is not defined. So it is kind of similar to sine graph. I'm only saying similar. I'm not saying same. Okay. So when my sine graph was, okay. So I have drawn my sine 1 by x like it is coming from this point and like this, and it's actually between 1 and -1. Okay, it's a problem with my drawing, don't bother. So when this is my sine 1 by x, there is a very slight difference for cos 1 by x. That is, here you can see it is moving towards this side and this is moving towards this side. But when you are drawing cos 1 by x, it will look like this. Okay, that is, the right side is almost same, but the left side is slightly different. The quadrants are different. Okay, so this is my cos 1 by x. So it has a similarity with sine 1 by x, that at 0, the oscillations are very close or very frequent enough that you cannot decide what is the limit at x equal to 0. Okay, so here for cos 1 by x, you don't have the limit. You cannot decide what the limit value is. So that's why I have put a question mark here. So it's we are unable to exactly say what g dash 0 is. All right. So we have that g is not differentiable at x equal to 0. Okay. So which means here we have f is differentiable at x equal to 0, while g is not differentiable at x equal to 0. So option A is the right answer. Okay. So how was this question? Did you understand? This is a very basic level question. So all what you need to know is regarding the structure of sine 1 by x and cos 1 by x. So at times you need to know what is the structure of the graph at times. Okay, I'm not saying always, but for certain graphs, it's good if you know the structure. Someone has raised a hand. Is it because you have a doubt or is it by mistake that?
No, ma'am, it's by mistake.
Okay, that's fine. Okay, so any doubts regarding this question?
No, it's clear.
All good?
Yeah, ma'am, clear.
Okay, so now we'll move to the second question. It's again a question from the previous year. So there you have been given a function. Okay, it looks slightly good enough, but slightly complicated. It's a combination of a polynomial, exponent, and trigonometric functions. The question is, how many local minimum do you have? Number of points at which the function f has a local minimum. So answers are welcome. You can take a minute or so to just work on this. So since the question directly demands a local minimum, we have already seen some theory part, so you know what to apply. So answers, okay, one of you has said A, which means there is no local minimum. Okay, any other answers? Again A, okay, yes, again A.
A.
Again, okay. So far no other option has come. So definitely this cannot be a multiple answer question because the numbers are given in a partitioned format. So 1, 2, 3 greater than or equal to 3. So like that they have given the option. So exactly one answer can only be there. So yes, so far whatever has come is A. Any other answers? B. For the first time someone has given a different answer. Okay, so no one has come up with C or D so far. So the person who has given option B, is it comfortable for you to just explain what you have done to get that answer? Because since you had a difference of opinion, can we just see what is the idea? Only if it's comfortable for you. If not, I can continue with my explanation. Okay, I don't think she is responding to it. So maybe I can help with that. So yes, so we are asked for local minimum. The question is very direct. You have been given the function. So this is my function here. Okay, I've just rewritten that. And then what do? You take the first derivative, right? So you took the first derivative, and what happens now? So when you say answer as option A, which means that there is no local minimum, why is it that there is no local minimum? Any answers? I guess the questions have started troubling you.
I think there is a to the power x, and the a to the power x is an increasing function.
Okay. All right. Okay. So there is something here, a small trap over there. So you can see that I think most of them landed to this answer because f dash doesn't become 0. That is the idea I think you landed up in. That's why you got that the answer is option A. So let's say, okay, let me keep my f dash there. I'm not trying to find out the zeros, but I am trying to find out my f double dash as well. Okay. So here I have taken my f double dash as well. All right. So now what happens next?
E raised to x is an increasing function.
Yes.
Sin 2x is a bounded function between -1 and 1. Cos x is also a bounded function.
Yes. So we'll just
And
write those details here. So 20, let me write it as such. So e power x is always positive. And for sin 2x, what will be the range of this function? So that will be -4 and 4 closed interval. And again, cos x, what happens? We will have -1 and 1. Okay. So now can you find something from this? What will be f double dash? Can it be positive,
it will be
negative,
positive.
0?
It
What?
will be positive.
It will, yes, it will always be positive. Because let's say I am taking -4 here for the worst case. And I am taking -1 here. Again for the worst case. But here I have a number large enough as 20. So it will be something like 15 plus something here. So which means f double dash is always positive. So what can you say about the shape of the graph?
Concave up.
Concave up. So what will it be? It will look like something like this.
Yes.
So now what can we say about minima?
One local minimum.
Exactly. We have only one local minima. All right. So there you see there was a slight small trap in the question. So you stopped at f dash and now you didn't get a 0. So you stopped there. So it's okay. It's just to verify. You just check whether what is the shape of the graph. Okay, because in some complicated cases, see, it's just that you are not able to compute it manually. You don't know whether if you're putting it in some calculator, you will get an x equal to 0. You're not sure about that. With respect to manual calculation, you cannot find the point at which f dash is 0. That's it. Okay, because it involves trigonometric, exponential, all those things, you cannot compute it manually. That's all. So what you can do is just take f double dash. Anyhow, even if you get f dash, you have to take f double dash, right? You have to check whether it is maximum or minimum. So just go ahead with f double dash. So with respect to that, you have got the idea. So you got that the graph is always concave up, something like a parabolic graph or something like that. So for such a graph, it will always have a minimum. It will not be local, but it will be an absolute minimum. But anyhow, you have only one minimum there. So is the idea clear?
Ma'am, could you
I
please
think
explain why is it 1? I didn't get it.
okay. So when we are finding the local minima, the process that we are doing is we take f dash, we check the points at which f dash is 0. Okay. So here, since we have a combination of functions, it may not be manually possible to find out the point at which f dash is 0. But that doesn't mean that it doesn't have a 0. It may have. Okay, because we have small enough value for e power x. For certain values, we have small values. Okay, so maybe for some value there may exist, but since it is not practically possible to compute f dash, what you can do is just take f double dash. Anyhow, you should compute f double dash, because if you get f dash equal to 0, you have to check whether it is maximum or minimum. So what you can do is compute f double dash first itself. So you got f double dash. So there you got that this value is 20. That's a constant. E power x, since our domain is not defined. Okay, anyhow, e power x is always positive. So there you have e power x is positive. Then 4 sine 2x, its range is always between -4 and +4. And for cos x, it is -1 and 1. So then even when I'm taking the worst case for these two trigonometric functions, it can be as less as -4 and -1 respectively. All right. So which means when I'm trying to take the overall sum, so you don't have any minus here, everything is summing up. So when you're taking the sum, it will be 20 -4 -1 plus some positive value. Okay, so that will be 15 plus some positive value. That means f double dash is always positive. So which means the graph will be of the form concave up. All right. Is the idea clear now?
Yes, ma'am. Understood, ma'am.
All good?
Yes, ma'am.
Okay, so let me just conclude that. So f double dash is always positive and hence concave up. And thus we have answer is option B, 1 local minimum. All right. So now we move to the third question. Again, a question from previous year. So last year there were plenty of questions from derivatives. I have filtered out 4 questions. There were other questions also, I guess. So this is the third one. So f be a twice differentiable function such that f of 0 equal to 0, f dash 0 equal to 2, and f of 1 equal to -3. Then which of the following is or are true? So this is the question. So answers are welcome. Okay, option A has come. Okay, any other answers? So this question, I'll give you a small hint. So this question requires some additional thinking. Not only what we have discussed so far, you need some additional thinking as well. Is the question not available on the screen?
Question is available, ma'am.
I think the person who has put the message, I think you should just check your internet connection once again. Maybe it's some kind of a glitch. Okay, so any answers?
Ma'am, is it a multiple option answer or just a single?
I don't know.
Because I guess two answers are getting. I'm getting two answers. I'm not sure. I'm getting B and C. I don't know why.
You are getting B and C. Okay. All right. We'll see. Okay. Any other answers? See, when you're given a multiple answer question, in that particular section, you can have single answer as well. So in that section, it's probably not easy to identify whether it is one option, two option, three option, or four option. So anything is possible. You can treat all my questions as multiple answer. Okay, so A and C has come. Someone else told B and D, right? Okay, so contrary answers are coming up. All right, so C is coming. Okay, so can we just check the question? So we have some conditions. So we'll start from the very first thing that is given in the question. So what is given? F is a twice differentiable function. So I'll start with that. Okay, so how does a twice differentiable function look like? Can you give me some example of a twice differentiable function?
X square.
X square, okay.
Sin x.
Sin x, okay.
Cos x.
Someone has unmuted by mistake, I guess. Not for sharing the answer. Please check. Okay. Okay. So what was the answer? What were we talking? Okay. Example twice.
Cos x.
Okay. Cos x, sin x, x square. Okay. All right. So now these are all twice differentiable. They are infinitely differentiable as well, right? So we have some conditions other than these. That is f of 0 is 0, f dash 0 is 2, f of 1 is minus 3. So you have to find out a function, or maybe you can just try constructing a function which satisfies these conditions. Then maybe you will be able to sort out the things. Okay. So let me say I'm going to take a quadratic polynomial. So quadratic polynomial is always twice differentiable. So since we don't know which quadratic polynomial satisfies these conditions, I am going to give a general polynomial for that. That is f of x equal to a2x square plus a1x plus a0. Okay, I've taken a general thing. So now you have certain conditions given, right? So the first one was that f of 0 equal to 0. So what will that give?
A2x square plus A1x plus A0 equal to 0. Or in other words, x into A2x plus A1 is equal to minus A0.
Okay, what is the final thing? What is the conclusion from that calculation you get?
A not equal to 0.
A0 equal to 0. Yes. So my A0 becomes 0. So my function f of x has changed to this form. That is a2x square plus a1x. Okay. So now we have two more conditions. Let's say I am going to take f dash 0 equal to 2. What do you get?
A1 equal to 2.
A1 equal to 2. Yes, exactly. So we got A1 equal to 2 as the second, after applying the second condition. So I replaced A1 here. So it became A2 x square plus 2x. So I have one more condition and one more variable to be calculated. So that was f of 1 equal to minus 3. So maybe you can make use of that and find A2. So what is A2? Yes, I need a final value of A2.
Minus
1.
5.
Minus 5. Very good. So yes, that is the answer. So now I got a function.
Ma'am, minus 5. Minus 5.
Yes, very good. So now I got a function which fits to the condition of the question. So it is twice differentiable. F of 0 is 0, f dash 0 is 2, f of 1 is minus 3. So I got a function which is fitting to the conditions of the question. What next? We have been asked about, what all are the things asked? F dash x and f double dash of x. What can you say? So let's find f dash of x. Find both these. What is f dash x and f double dash of x? So f dash x becomes minus 10x plus 2 and f double dash x becomes minus 5. Yes or no?
Yes, ma'am.
Yes. So now in the question, you have already been given the intervals. Let me just check the interval. Okay, just a sec. So it's from 0 to 1. Okay. So now what can you say? Between 0 to 1, what can you say about these two?
Ma'am, double differentiation is minus 10. I think.
Yes. Sorry. That was a mistake. I'm sorry about that. Okay. Thank you. All right. So now they have asked about modulus of f, I guess. Oh, I think this was a mistake. I should have written the question somewhere else parallelly. Okay. So the question is concerning modulus of f dash and f double dash. What can you say? So let's see the next step. I have computed my f dash and f double dash. So our range, the domain is from 0 to 1. So when it is from 0 to 1, f dash will be from, so when x equal to 0, f dash will be 2. And when x equal to 1, f dash will be 8.
Minus 8, but modulus, since it's
Yeah.
modulus value, we'll take it as 8.
Yes, I missed the modulus. Thank you. And f double dash, when you're taking the modulus, it directly becomes 10. So keep these two things in hand. So that is what gives the answer. So what is the options here? F dash of x is less than or equal to 2 for all x? No, because we have 2 existing here. So you have option B is right. And f double dash, what happens? For all x, is it less than 10? No, we have it is equal to 10. So the answer is option D.
Ma'am, how is we collect f dash mod is greater than 2, but it's equal to 2 in our solution?
See, here it is for all x. Okay, here the question is for some x1. So we have some x for which this is greater than 2. But you don't have all f dash value less than 2, right? So you have to be careful. When you're looking at the option, make sure that you're looking at the quantifiers. Whether is it for all, for some, there exist, for all. See, all these things you have to check.
Yeah, ma'am.
Okay, so these quantifiers are slightly troublesome. Don't jump into the answer. Read the option once again. Check whether is it for all or for some, and then go to the answer. Okay.
Ma'am, this type example we taken as some other example we used in examination, or this is a.
See, you're free to make use of any example, but make sure that it satisfies the condition given in the question.
Ma'am, why it is given as for some x1 belonging to closed interval 0, 1 in option B? Like, isn't it possible for everything, every value coming in that interval?
Yes, definitely.
Dash of x.
Yes, definitely. But see, this for some is slightly relaxed thing. That's it.
Okay, fine. Okay.
That's it. You don't have to pay too much of tension on that. It's just a slightly relaxed statement. That's it. All right. Okay. So the person, I was already speaking to someone. Okay. So when you are taking a function, you already have some constraints in the question, right? You have f of 0, you have f dash 0, you have f of 1. So with respect to that constraint, if you are able to construct some other function which satisfies this constraint, then it's fine. But if you are taking some other function, let's say you are taking some sine, cos, or some other function, it may not be this easy. Taking a polynomial, and since it was a quadratic polynomial, finding the coefficients was far easier, isn't it? So that's why I have stick to that idea. If you have some other function which satisfies this condition, then you're free to use that. No problem at all. Okay. So can we move to the next question?
Yes, ma'am.
All right. So next
Yes, ma'am.
question is this one. It looks very similar to the one we have done just now. And the funny thing is that these questions have come. Yes.
in this problem, sorry, I am trying to say that the previous problem.
Sorry.
Let's go to the problem.
Oh, this problem.
Yeah, yeah.
Okay.
Yeah. Here, I am following your logic, but you have chosen the function second degree only. Okay.
Yes.
But can it is possible to solve it properly? I think if we are asked that comment on the probable values of f double dash x. Suppose you have not given to these four options, then can we solve this? It is the way of solving during exam, okay. But is it possible to solve without this option?
Is it possible to solve without the function? It may not be that easy because you don't know anything about the structure of the graph. If you know the structure of the graph, maybe something you will be able to predict, because then only you will know what is f
And
dash and f double dash, concavity, decreasing, increasing, all those things. So since you don't have any such details except the value of some function values and derivative values, you don't have anything else with you, right? So it may not be that easy. I think this would be a better way of doing it. I don't know if you have used some other logic, and if it's less time consuming.
yes, ma'am, I'm using, and my option is successfully E and D, but how much it is rigorous, I don't know. Can I say here what I am using?
Yeah, or go ahead.
Yes, I am considering just double use of the mean value. Okay, and one mean first using mean value 0 and 1, then you will get a point between 0 and 1. Suppose let's it is say C.
Okay.
Then using mean value 0 and C.
Is this what you're trying to say?
Yes, yes.
Okay, so it becomes -3 minus 0 by 1, which is -3. Okay, all right. So then you get that for some value there is f dash greater than
Greater than 2. Okay.
Yes. Okay, very good. And for f double
and
dash?
now I am telling and this point for using LMPT first time I am getting their existence of sub point called it is C. It is lying between 0 and 1. Okay. At least 1 point C. And now again applying LMPT between the interval 0 and C. Yeah. Then you will get the point D option as.
Okay, that's good enough. Very good. So he has used the idea of mean value theorem there. So that is also possible. Okay, very good. Your name was, sorry, I didn't see your name.
I'm supporting.
Okay, okay, thank you. All right, so now can we move to the fourth question? So this is the fourth question. So this question was again from 2025 JAM exam. It looks very similar to the question we have solved now. And the funny thing is these two questions were adjacent. Like one question was question number 37, this was 38. So can we try solving this now? So if you have answers, you can start posting it. None of these. I don't think that we have
Extra
an
option. Extra option should given there as none of these. Option E.
Okay. So why is it that it's none of these? So here the problem is, since we have solved a question similar to this before, we have a tendency to apply the same method here. But unfortunately, that method doesn't work. So any other ideas?
I guess we can go for mean value theorem somewhere.
Yes, mean value theorem is required. Okay, so with respect to mean value theorem, what do you get?
Let me see, ma'am. I'll tell you soon.
I mean, option there is two type of interval, 0 and 0, 3.
Yes.
Then we can apply in this interval, then we get something.
Yes, so how can you get that? B, C, D. Okay, so one answer has come with multiple options. Any other answers? I feel sad that I'm running out of time. Okay, it's already 7:50. I have reached only fourth question. So can we make it a bit fast? Answers are most welcome. So mean value theorem or Rolle's theorem, whatever, that is one option. So you can see two options. They involve mode of f dash. So these two are like kind of.
Ma'am, option B is right.
Okay. And remaining. One is simply f dash, not modulus, and another one is f double dash. So you have to check all these. What can you do? So I'll slowly start explaining the answer. You can continue doing it if you feel like going along. Okay. So here.
Ma'am, I'm getting only B. I don't get any other thing.
Okay.
I'm just
No
getting
issue.
B.
No issues. We'll see what all answers we are getting. So I have 3 or 4 conditions here. You see f of 0, f of 1, f of 2, f of 3. Okay. So I'll just try to draw this graph. Okay. So I have 0, 1, 2, 3. And let's say I have minus 2, 2, 4, 6, 8. Okay. Let me take a different color. So at 0, my value is 4. At 1, my value is minus 2. 2, it is 8. And 3, it is 2. Okay. So the function is already given to be a twice differentiable function. So definitely it is continuous and a smooth curve, right? So I'm just going to join the points. Okay. It doesn't look that good. Let me see whether I can just draw it once again. Okay. So now can you say something? I'm not saying that this is the function structure. I'm giving a possible prediction. Okay. It can be like maybe like this. Okay. That is also a possible structure. But I have taken the simplest possible one. Okay. Let me keep my yellow graph aside. So I've taken the simplest possible structure. So what can you say about this?
In the interval 0 to 2, closed interval 0 to 2, the function is strictly increasing. I mean, It's concave up. The graph is concave up.
Mm-hmm.
And in the interval 1 to 3, it is concave down.
Mm-hmm. So what do you have there? So concavity has changed.
Yes.
So what do
So
we have?
1 point of inflection.
We have a point of inflection. So what do we have at point of inflection?
F double dash of x is 0.
F double dash of x is 0. So which means in this particular interval, I have some F double dash for which a point for which F double dash is 0. So now we have option D. And what about option C? F dash equal to 0 for some value. Is it possible here? You can see that the graph has decreased, increased, and then again decreased. So you have some local maxima or minima there. Right. So here you have this point and this point. So you have local maxima and you have local minima. Right. So which means our f dash value is 0 at some point in that whole interval. Right. So now what we have is that we have option C and option D are correct. And some of you have already given option B as the answer. And that we can do it using mean value theorem. So yes, let me just conclude the things that I've just drawn. So from 0 to 1, the graph changes its concavity. So we have f dash equal to 0 for some x in that closed interval 0, 3 and f double dash also. That is, let me just repeat my point. So here I've just drawn a graph that satisfies the condition. That's it. Okay. So I've drawn a smooth curve that satisfies this condition. Since the graph has decreased to some point and then increased to some point, I have a local maxima and a local minima. Or you can just take it like this. At this point, f dash is decreasing. Here, f dash is increasing. So it should definitely have some point at which f dash is 0. All right. So there you have f dash x2 equal to 0 for some x2 and f double dash x3 equal to 0 for some x3. So you have C and D are right. Now for the third part, we'll make use of the mean value theorem. So this was what I was saying. At some questions, you'll have to incorporate multiple ideas. So for option A and checking A and B, you needed mean value theorem. But for C and D, it has got nothing to do with these theorems. You have to get some idea about the structure. So whenever, let me give you a hint, whenever you have a question like this, questioning whether f dash is 0 or f double dash is 0, you should have some idea about the structure of the graph. That is there some possibility for maxima or minima or point of inflection? So these things are very important when these kind of options come. All right. So now for option A and B, we are going to make use of the mean value theorem. So I have a C for which f dash C is of the form f of b minus f of a by b minus a. And here we already have f of 1 and f of 0. All those things are given in the question itself. So it is minus 2, minus 4, and after the substitution, you get f dash c equal to minus 6. So my mode f of c becomes 6. So what will the answers be? Here we already got C and D. So we have f dash is greater than or equal to 5 for some x. We cannot take this one, first option, because it says for all. We have already obtained a point at which f dash is greater than 5. So we cannot take option A. Option B is the right answer. So is the idea clear? No responses.
Yes, ma'am. Yes, it was clear.
Yes, ma'am. Yes, ma'am.
All right. So even though the questions 2 and 3 looked similar, you can see that the approaches we used were slightly different. For one, you found out the function. Okay, even if you're not using that idea, you can obtain the answer. But for the fourth one, we need some idea about the structure. Exact idea is required. Okay, so like I said, let me repeat my point. It depends on the question and options that what idea you should be giving as input. Okay, so now question number 5. Global minimum value of f of x. So f of x is given. What is the global minimum value? So this is a numerical answer type question. You don't have options. So what can you say? I think we should be speeding up. There is an exam at 8:30. Maybe I should wind up at least at 8:15. So answers, we can make it a bit fast. So if you have any answers, I'll listen to that. Otherwise, we'll move to the options, explanation part. Okay, someone has given the answer as 1. Okay, you can put the answers in the comment box. I'm checking it parallelly. Okay, so here you have been given function f of x. So it is the sum of 2 modulus. Okay, even though 1 is square of it. So first thing what you can do is you can just split this function into different domains, right? That is, you can just split it and write it in this form. So I have x minus 1 plus x minus 2 whole square. So square, it's already positive. So I am not taking the modulus thing. I've just taken it as merely square. So that is the case when x is greater than 1. 1 minus x plus x minus 2 whole square if x is less than 1. And for 1, when you're just substituting, you will get it is 1. And for 2 also, x equal to 2 also, here either of these you are free to put the answer in that. So you'll get the answer as, so here x equal to 2. Here you can substitute 2. So this becomes, oh, sorry, not this one, greater than 1, right? So in this one, so if you are putting 2, this becomes 0, this becomes 1. So you get 1 when x equal to 1 and 2. So the question is concerning global maximum global minimum on the entire real numbers. So what you can do is to find out the local maximums first. Minimums first. I am just confusing between this maximum and minimum. Okay, let me stick to minimum itself. So how do you find a global minimum? You'll have to list out the local minimums. Among that which is minimum, that will be my least value, will be my global minimum. So I have to find out the values at which f dash becomes 0. So let's just do that. So f dash, let me forget 1 and 2 because you already know function value at 1 and 2. So you are not bothered to calculate function value at those points. So let's say I am trying to find the derivatives at the remaining part, x greater than 1 and x less than 1. So I got 1 plus 2 into x minus 2 when x is greater than 1 and minus 1 plus 2 into x minus 2 if x is less than 1. And now you have to find out the possible values at which f dash becomes 0 in both these domains. So for x equal to, so in the first one, that is this one, you get that x equals 3 by 2. You can just solve it by mere calculation. Okay. And now for the second part, what will it be? This one. So after solving that, you get x equal to 5 by 2. So here there is a small mistake which you should be looking at. Here you can see that this value is greater than 1. This is also greater than 1. But where have we taken this from? It is from the case where x is less than 1. So can we take x equal to 5 by 2. 5 by 2 is exceeding 1. But this particular function is when x is less than 1. Okay, so which means I cannot consider this possibility at all. So I need to check only this one. That is only at point x equal to 3 by 2. I need not check at x equal to 5 by 2 because that is entirely contradicting my statements. Okay, so now what do we get? Already we have f of 1 and f of 2 as 1. And then f of 3 by 2, we have it as, so I have just substituted it. So when you're taking f at 3 by 2, you have to take this function because it is greater than 1. So you substitute in that, you make the calculations, the final answer that you get is 0.75. So you have 1 and 0.75. So you have listed out the minimums, possible minimums. So what is the global minimum value? It is 0.75 itself. So that is the final answer, 0.75. So is the idea clear?
Yes, ma'am.
So here the only thing that you should pay attention to is this thing. This will land you in some mistake because you got x at which f dash is 0. You continue to compute function value at that point, but it doesn't match. These two things doesn't match. So you have to exclude that point. So that is one possible mistake that can come in this question. Okay, so there are very small things. So the question looks very simple. Computation is also simple. Idea is also simple, but one small mistake, you will end up in a wrong answer. Okay, so that's it about this question. Now we move on to the sixth question.
Ma'am,
Yes.
ma'am, here you take the one condition, one is less than, x is less than 1 and x is greater than 1.
Yes.
Why not 2? I think 2 is included in this interval.
Yes, yes, definitely yes. See, what, let me just take that slide. Okay, so here, let's say my function is this one, right? So what do I have? I have 1 and 2. So here, less than 1, it is x, sorry, 1 minus x and x minus 2 the whole square, right? Here it is so, okay, let me not move into a very detailed explanation. The only reason is because you see here it is square, right? So when you're taking a square, whether this value is positive or negative, it doesn't matter. Even if you're changing this x minus 2 or 2 minus x, it doesn't make any difference. Okay, so that's the only reason why I have taken it as a whole square. That's it. Okay.
Yes, ma'am.
All right. So now moving on to the next question. Sixth question. Okay. So here, this is the question. So I have a set of functions which satisfy a particular condition. Okay. Then which of the following is or are true? This is the question. So I think I am still running out of time. So I think I should just continue to the explanation. You can just work it out by yourself. Okay, I'll just show the question. I'll move to the explanation part. Okay, for the upcoming questions. Otherwise, I think I can't end it up even by 8:15. So this is the question. So I have a condition given. That is, f is a set of all functions from real numbers to real numbers satisfying mod f of x minus f of y whole square is less than or equal to mod x minus y whole cube for all x and y belongs to R. So this for all is also very important. Okay. So there I am just putting up the condition that is given in the question. So I have taken square root as a whole. So the function becomes mod f of x minus f of y is less than or equal. So I have taken by 2, right? So this is how it will look like. In the next step, I am taking one mod x. So this will be mod x minus y into mod x minus y power 1 by 2. So in that, I'll bring this mod x by x minus y to the left side, and it will look like this. Okay, so it will be mod f of x minus f of y by mod x minus y less than or equal to mod x minus y power 1 by 2. So I've made that modulus as one single whole modulus, a large enough modulus. In the next step, I am going to apply limit to both sides. So you have that when you are applying limit on both sides, since it is less than or equal to and it's a modulus function, I can maintain my limit condition. So that is, limit will also satisfy this inequality. So I have given limit outside. In the next step, I have just taken this limit to inside, because for modulus function, it's not a problem. So now what you can see is that this is same as f dash y, right? The basic function definition of derivative. And here x is tending to y, this becomes 0. So here I have that f dash y is less than or equal to 0. Since it is modulus, it definitely cannot be less than 0. So the only possibility is that f dash is 0 for all y. Right. So here this for all y comes from the condition in the question. So we have for all x, y belongs to R, right? So carrying over that condition, I have that derivative is 0 at all points. So what will the function be? It will basically be a constant function. So which means my f is a constant function. All right. So constant function, what do you know based on the options? So every function, so every f has to be a constant function. So you can give different constant values. So you have that every function is differentiable. So there exists a function that is differentiable but not twice differentiable. That's not right, because constant function is infinitely differentiable. So that is right, and this is wrong. So these are the answers. Any doubt on the explanation part?
No, no. Here one point is that you are putting the limit inside the modulus function because of it is modulus function is continuous and this interchangeable limit is persistent.
Yes,
That is the
exactly.
okay.
Yes. So I hope the explanation is clear. Can we move to the next question now?
Yes.
Okay. So this is the next question.
Yes.
So this question is slightly tricky. It may mislead you for a point. Okay. So f is an infinitely differentiable function such that for all AB belongs to R with A less than B, f of B minus f of A by B minus A equals f dash A plus B by 2 dash. So the question is regarding what is f? Is it a polynomial or not a polynomial? If it is a polynomial, what can its degree be? This is what the option concerns. Okay. So this question is slightly misleading because once you see this thing, you have a tendency to jump to mean value theorem. But the thing is that this is nowhere related to mean value theorem. Okay. So now let me move to the explanation part. So what I have done here is I have just taken a very simple example and I have eliminated all the three options. I have landed in one single answer. So let's say I am taking the polynomial function or the constant function. So when I say f of x equal to c, that is a polynomial, constant polynomial. Okay. So with this, you can strike off three options. That is, let's first check whether this function is satisfying this condition or not. So it is infinitely differentiable. And for any 2 points, f of b minus f of a will be 0, which is same as f dash value. Okay. So this function is satisfying the condition given in the question. So we have that f is not a polynomial. Need not be. I have already given an example which is a polynomial. So this is not the answer. Then f must be a linear polynomial. I have given a polynomial which is not linear. So again, this is not the answer. Then f must be a polynomial of degree greater than 2. So for constant polynomial, degree is 0. So again, this option is not right. And this is the right answer. So this is where I said in the beginning, sometimes some examples will help you to strike off the wrong answers. But choice of example is equally important. Okay. So is this idea clear?
So thank you, Nandana, for this nice session with a good collection of problems and the most recent problems. Many of the problems are from JAM examination of last year.
Yes,
So
sir.
I'm sure that our participants have gained some confidence to crack the IIT JAM examination of this year. Okay, dear participants, it is your time to share your feedback. Feel free to share your comments about the session.
Hello. Yeah, good evening.
Ma'am, I'm Archana. I have completed my BSc. I'm trying for JAM this year. Ma'am, I really
Okay.
enjoyed this session, like including how you like explained each and everything in detail. Your voice was very calming and it was like very smooth. Like we could hear it in a very pleasant way. Even if the question was a little crazy, you helped us calm like down and explain the questions individually, even if the questions we had doubt.
I don't know whether I was just rushing too fast. I don't know.
No, ma'am, no, ma'am. It was actually in a really good pace. You gave us time for the question, for us to do the questions also. Yes, ma'am.
Okay.
Ma'am, I really
Thank you.
enjoyed the session. Hoping like that you take more classes. Thank you, Vinod sir, for arranging this session.
Okay,
Thank you.
Others?
Good evening, ma'am.
Good evening.
Ma'am, my name is Varada. I have also completed my BSc and like right now I'm trying for JAM. So I also I thoroughly enjoyed today's session. Like even though the time has surpassed, like I didn't notice it, to be honest. Like as Archana told, all those things that you explained, it was in a very calm and composed manner. And like you didn't rush actually. Like I didn't felt so. You made sure that each and everything that you explained was properly understood by us. So it was a very engaging and comfortable session, I would say. So thank you so much, ma'am, for this great session. And I'm hoping to see more such sessions with you in the future.